our course name is Special Topics in Civil Engineering, so it's risk and reliability. Risk and reliability, actually, it's one of the classes that sometimes are taught in university as a core courses, not special topics, has basics and has everything. But since we will not only focus on the risk and reliability, we will focus on the applications more than the theory and the science itself. So it's a special topics. And the content for this class. Okay. So we will touch base today. I'm just going to give you guys a presentation on how the concepts that we are going to learn in this class will help us in research. I'm going to show you some samples of research that are based on risk and reliability concepts. So you guys can have some ideas that inspire some research topics that you can work on for your dissertation. Maybe you have like something new that you can work on. So this is just like an introduction. I'm not going to start the course today. So just like general idea, how the risk and reliability research can help you or helped me in the past to develop my research and my PhD and moving forward until now. Okay. And then starting next lectures up to lecture number 14, we will touch based on the basic probability concept, like the probability theory, what is the definition of probability, what is the bias theory, and what is the function of random variables. And then we will spend 1 week on the probability laws, what are the probability laws, what are the different types of extreme distribution, type 1, type 2, type 3 distribution. We will learn all these distributions together. And then we will spend another week on the classical reliability theory and a week on Monte Carlo simulations. So these all concepts that we are going to learn together, and 1 week on the first order reliability. So these some basics that we are going to learn in this class, maybe until week number 7. So we will be learning some basics. It will be I'll try to make it interesting a little bit, but you know, probability, we are engineers. Most of us are not interested on the probability, but you know what? Probability is the basics of everything in engineering. Like when you design or when you calculate loads on buildings, it's all based on probability. So what is the probability of having the load in the code here right now? So the code loads is based on probability, okay? And also the design is also based on probability. Like when you design, it's all a matter of strengths and resistance. And strengths and resistance are uncertain quantities. Like it's not deterministic quantities. And I'm going like to just show you an example, just very quick, but we will go in detail. I'm just like want to let you know how this concept is related to what we are doing. Like, are you guys familiar with this curve? This is the normal distribution, right? So this normal distribution, if you have some data, and sometimes this data can fit as a normal distribution, like you have, and also it has different shapes. So this is called continuous probability. Sometimes it has discrete shape, like you have some bar chart, something like this. And this is called discrete. But by the end of the day, it's the same thing, same concept. If you fit this as a curve, it will be something like this, right? A normal distribution. Same thing when we talk about the resistance of an element, like when you say like, okay, this beam has a resistance of 50 Pascal or has a resistance of 5 ton or 10 ton. So this resistance, you made this assumption based on some parameters of this, but this parameters has some uncertainties. And when you say the resistance is this value, this is the mean value. And there is a standard deviation behind this mean. Like this, if you are saying it's 5, okay, it could be 4, it could be 6, it could be 4.5, it could be 4.6, but I give you the mean value that you can design on. Same thing when we talk about loads. The loads of this building, the live load is like 100 kilogram per meter square. This is the mean, but it could be 110, it could be 120, it could be 90. So it can goes up and down. So we are talking about mean and standard deviation, not deterministic quantities, but are probabilistic quantities. Okay, so this is what we are talking about. And when we design, like, let's let's assume that we have a column, something like that. And this column has load B, and this B, for example, has mean mu is equal to 10 ton, but it has also standard deviation. We will learn what is mean and what is standard deviation, but just like I'm giving you an example, has mean of 2 ton, like, and here we are talking about loads, but also this column has resistance. This resistance has a value. If the resistance is less than the load, this column will fail. But if this resistance is more than the load, the column can't resist the load. So when we represent this as a relationship, so this, what we want to do is we want to have the loads, the normal distribution of the load like this way, and the normal distribution of the resistance be something like this. And what this means? Like, for example, if this is the load, this is the load, and we are saying this load is 10, we need the resistance to be maybe 15 or something, the mean. But if this 10 increased to be 20, the failure will happen. And the intersection here, when we say this is 10, the load can have the mean value of 10, but there's a probability, a very small probability, maybe 1%, that this load is gonna be, for example, like 13. Okay, and the resistance is 15, but there is a low probability that this resistance can be, for example, 12. This what we call the probability of failure. Like here, when the resistance gets very low, so you will start to have failure here. So that's what we are talking about. And we need to minimize this probability of failure. So here is the loads, here is the resistance. We need to make that the resistance is much higher than the load so that we can make sure. And this is the basic design of any element. When we design based on codes, we need to find what is the probability or what is the distribution of the load and what is the distribution of the resistance. And we need to minimize, maybe we can make the probability of failure 5%, but sometimes you want to make the probability of failure 0%. So it depends on how critical is your element. If you are designing a nuclear power facility, is different than designing a small residential building or a small commercial building. Each one should have different. So what we need to control is that we need to control this, the probability of failure. All right, so this is just a hint on how the concept of the statistics and probability and reliability is important in our field, because every quantity that we have in our field is uncertain. The characteristics of the reinforced concrete is uncertain. If you have like 10 cubes and you test them from the same truck, it will have different strengths. And also the resistance of this is like even the loads. Like for example, I'm 80 kilograms, somebody else will be 70 kilograms. If we both sit on the beam, we'll have different loads. So the loads is also uncertain. So those are two uncertain quantities, and we need to identify these uncertainties so that we can design these beams. So this is just like a brief introduction of how the concept of reliability and the concept of probability is very important for the structural engineers. But let me tell you now this is how this concept from lecture 1 up to lecture 14, how it help us to know how to deal with these uncertain quantities, okay? But what I added for the risk and reliability course, I added some content that makes this course a little bit more interesting to teach you some tools that can help you apply this concept. And that's what I usually do in my classes. I want to teach theory, but I want to teach my students how to view softwares, how to actually make a real product, okay? So we are going to learn some ArcGIS so that we can visualize data, analyze the spatial data, so that we can do community level analysis. So we will touch base on these. And also I need to teach you some hazards. This hazard could be wind, this hazard could be earthquakes, could be flood, but I will focus on flood and wind. So I will be focusing on these two hazards, but all what we are doing here can be applied to any hazard: tornadoes, earthquakes, the tsunamis, any hazards. And we will be doing exposure analysis, and we will touch base for a week or maybe 2 weeks on the fragility concept, because this is a very important concept in our field. And this is the trend. Maybe the standards are going to move to fragilities and natural hazards and all of these things. So right now, the standards are based on the strengths, but they are moving to performance-based design. Okay, we don't want to design that column to fail, but we want to design this column to perform in a certain way. So we need this column to perform, to have this certain level of performance that I will be satisfied as a user with this performance. But right now we are moving to the resilience, but not only the performance of the building, but what is the performance of the entire community? Like, for example, we got a natural hazard in a certain community and it's impacted the building. And what is the point of recovering this building? Like, let's say that we have some columns cracked, some walls are cracked, and you recover your building, start working to patch these cracks and recover your building and getting it ready, but you don't have power, or you don't have water, or you don't have service. So you will not be able to use this building. Or even you have power and water and service, but the schools are not working, your workplace is damaged, and you cannot access to your workplace, you cannot access to gas stations, so it doesn't matter. So recovering the building is related to other parameters in your community, and that's what we mean by community resilience. We need to understand how the entire community is function and depend on each other. Because yeah, we can build a building, but how other buildings serve my building, how schools, I have kids, I need to send the kids to schools. If I wasn't able to send my kids to school, I will stay at home. If there's no hospital, if I'm sick, how can I go to check with a doctor? If, like, for example, you work in some place or you need to shop, so there is no shopping centers. All of them are damaged from flooding or from earthquakes. So all this impacts your functionality as a building, and that's what we mean by community resilience. So that's what we are going to learn about. So we will study some single hazard fragility, some multi-hazard fragility functions, and we will see how can we develop mitigation functions, how can we reflect the mitigation into our vulnerability functions, how we are going to do some community level vulnerability analysis and some introduction about the community resilience analysis. So we are not going, because it's a very big topic, so I'm just like giving you some hints at how you guys start this in your research. And the course is, we will have 25% on homeworks, and we will have one midterm exam with 35% of the points from lecture 1 up to lecture 14. So for the first 7 weeks. And we will have our exam maybe in the 8th, 9th weeks, that depends on how far are we get in these topics. And we will have a final project. So everything that you will learn here, you will use it towards a final project. So you will choose maybe a piece of your research to do your project on. Some of you is working on wind, so you might choose wind. Some of them decide to use flood. I will help you, provide you some data, some hazard maps to start your project. Okay, and I will see if it will be single or you can do group projects. So we will see how we will figure this out. So does anyone have any question before I start my presentation? Does everything sounds good? Okay. Yes. All right. Okay. So let's see. Okay. So let's see how the topics that we will learn in this class will help us in natural hazard research. So what I'm trying in this class is to prepare you or train you to be a catastrophe modeler or a risk modeler. Okay, so the concept that I'm going to teach you is used in insurance companies and like catastrophe modeling companies. So if you put lots of effort in this class to learn the basic concept that we are teaching here, you will end up in like, because let me tell you, like, yeah, being a structural engineer is very good, but if you are looking money-wise and research-wise and more like things that are required to invade as a structural engineering in terms of natural hazard, these are the topics that you need to be, and you need to utilize your structural engineering skills to understand natural hazard modeling and catastrophe modeling and community resilience research. and they get paid more. So the average of structural engineer is less than risk modelers and catastrophe modelers. And if you end up in an insurance company, you will be way high than average structural engineers in the field. Okay, so this is just like one hint about it. But let's start the topic and let's first talk about risk. So what is our understanding of risk? Sometimes like people misunderstand the concept of risk. Like they say, okay, we have a flood hazard, we have a risk of flooding. And they only talk about hazard, but it is not only about hazard. Yeah, flood can happen. It has a frequency and it has an intensity. So when we talk about the hazard itself, so we need to talk about two things. What is the frequency of having a 1 meter flood depth at this location? Okay, when we do some statistics and run some data, and we will know that to have a flood depth of 1 meter will take 100 years, because we never had a 100 meter flood depth for 100 years. So it takes 100 years to get 1 meter. So how about 1,000 years? Is it going to be less or more? Like when we are talking about flood events. So when we talk about 1,000 years, this has lots of events. We could have 2 meters, 3 meters, much more, because there's a time for many hazards to happen. Okay. And if we are talking about 10 years flooding event, so 10 years is just a short period. So we are talking maybe 0.5 meter or 0.4 meter. This is just an example to imagine what is the hazard intensity at and what is the frequency. Frequency means like when this hazard can happen or how many frequent this hazard can happen. So 1 meter flood depths can happen once in a 100 year or once in 1,000 year or once on a 50 year. So this is what we say frequency. Okay. And the second thing is intensity, is the height of the flood. 1 meter, 2 meter, 3 meters. So this is intensity. But intensity could be referred not only on depth, but also velocity. Like we can say flood velocity is 5 meters per second or 3 meters per second. Also flood duration, like the duration can be 300 hours, 200 hours. This is also considered intensity. Some people use momentum as an intensity. So it includes velocity and other parameters. But when we say intensity, it means flood depth, flood velocity, flood duration, all these is called intensity. But frequency is how frequent the flood is happening. And all this is related to the hazard. Okay, so let's assume that the hazard did happen. But this is still not only the risk component. The hazard, it happened in a community, but there's some building exposed and others are not exposed. So we need to do some spatial analysis to know which buildings are exposed and which buildings are not exposed, right? So exposure is a very important element in the risk. So we say like, okay, the flood hazard happened. Okay, so this is the risk, but I'm not exposed. So I don't have any risk of being flooding, right? But if you are exposed, yeah, you have the risk of being flooded. Okay, so exposure is also one important element for the comprehensive risk. Okay, and also vulnerability. You might be exposed and you have flooding around your building, but you don't have vulnerability to be damaged. Your building is elevated and there is no water inside your home. So you are exposed and hazard happened, but you are not vulnerable, okay? Or you were able to construct a sandbags around your building or a flood barrier around your building and you didn't get any flooding in your home. So this is when we talk about vulnerability. Or you have your building elevated from the ground by 1 story and all you have flooding and you are exposed, but you are not vulnerable to have damage because your building is already elevated from the ground. And this is the third element of vulnerability. Same thing applies for all the hazards. Wind, earthquakes, you need to account for all these components: hazard, exposure, and vulnerability. So you need to have a hazard map to know what is the exposure is and to know what buildings are exposed and what is the level of exposure, what is the hazard intensity. And you need to know all this information about the hazard. And then based on the building type, some buildings are strong enough to resist the earthquake, but some buildings are poorly designed and they are more vulnerable to have damage, right? So this concept applies for all the buildings. So we need to talk about hazard, exposure, and vulnerability. Don't forget these 3 main elements of risk, okay? All right, so, and then let me talk to you about, so most of us and most of structural engineers are doing research at the building level and maybe at the component level. Like I believe that most of you might start research is studying, for example, let's assume that we have a home like this. All right. And I believe some of you can do research for years, only studying one component, like maybe studying what is the wind impact on this part, or they are studying the connection between the walls and roofs, like what clip that I can use and how the different clips can impact the wind resistance of a home. And some of you can study the shingles of a home, like how the different nails type can impact the resistance of these shingles to be to resist the wind loads on these shingles, right? So this is called component level analysis. And when you integrate this component level to inform some information about the building, we call this as a building level analysis. So when we do component level analysis, for example, we can develop a vulnerability curve for this connection. Like you have something like, for example, wind speed V, and this V is like 30, 40, 50, 60 meter per second. And here is the probability of damage. And you have a curve like this. So if you have a wind speed 50, you have much higher probability of this connection to be damaged. If you have wind of 20, this has a 0 probability that this connection is damaged. So you can do this for this component. You can do this for a window. You can do this for a door. You can do this for the wall itself, for the roof, for the shingles, for the panels, for the trusses. You can do this for every component and get a curve of what we call it a vulnerability curves that can tell you what is the level of damage that you will have if you got hit with this wind speed. What is the level of damage that you will have if you got hit with this flood depths? What is the level of damage that you will have if you got this level of a spectral earthquake acceleration? Okay, so we call this vulnerability curve. Okay, so if you did this for components, we call this component level analysis. But if you were able to integrate the vulnerability of all the components within the building to tell the performance of the entire building, we call this building level analysis. But we can use this to inform information about the community. If we were able to do this for each building within the community, so we are doing community level analysis. So let's see how we can stage from the different levels of resolution, from component to building to community. We need different types of information. We need community level data. If we are talking, this example is for flooding. You need, like, for example, digital elevation map for all the study area, because the elevations in the study area tells you where's the flood is going to be. It's going from the highland to the lowland. You need to know the land use, the soil, because the amount of water surface flooding, like the surface water flooding, depends on what soil type. If you have a very loose soil, the water can goes in, so the soil can take lots of water, and you have less water in the surface. But if you have pavement, if you have concrete, it takes less water, so you will have. And also the land use, like the forest is different from the locations that has lots of buildings. So land use and soil, all these informations are very important when we deal with flooding. And also same thing when you do with earthquakes. So earthquakes, the same thing, depends on the soil and how the earthquake waves moves within the soil. So you have also needs information about the soil. Same thing for wind, it depends on the exposure. If you have an open ocean, like an open exposure, like open water exposure, there's different levels of exposures. So you need to know what is the exposure level that you have. And based on this, like communities that doesn't have buildings, is less than open communities. Like you have a desert that doesn't have any buildings. So all this, so you need information at the community level. Also at the building level, you need information about the buildings. Like where is the building? What is the building location? Because the building location will tell you what is the exposure. Because if you are close to the river, it's different if you are away from the river. Also the vertical floor elevation, because you might have your building on the ground, but how about building elevated from the ground by 1 meter? By 1 story. So you need lots of information about the buildings. About the components, you need to know what component types that you have. What is the resistance of these components? Like, for example, when we talk about wind, how many nails in these shingles? Is it 1? Is it 2? How does this connection look like? Does the building is using a hurricane clip at this connection or not? So all this makes difference. So you need to know lots of information about the component. And then with this information, you can integrate component level with building level and with the community level up there. Because community is a bunch of buildings from 1 to n, and each building has a bunch of components. And if you started at the component level, you can stitch your research from the component to building, and then from building to the entire community. So this is an example of what I did in my research was flooding. I was able to get component level fragility or component level vulnerability function for each building that can tell me how much damage each component can have at each flood depth. And from the component, we're able to develop a flood fragility for the entire building. So for example, if you have a flooding in your home and you have the carpet is wet, okay, I can leave my building for 1 or 2 days and I like if it's just a little wet, so it will dry out. But if it's very, very wet, okay, I can replace the carpet and reoccupy the home. It's completely different if you have 1 feet of flooding and you have all the appliances are damaged and all the dry walls need to be replaced. It will take lots of time for recovery. So each one of these is different. So we can make a specific, what we call damage state, slide, moderate, complete, or extensive, complete. And based on the component damage, we can know what the building, what is the state that each building at. Is it a slide or moderate or complete? And we can get some probability of being in a slide or moderate or complete damage state. So this is what the concept of fragility that we are going to learn. It's a function that can tell us what is the probability that this building have a slide damage state. And what I mean by slide damage state is the carpet is wet, is the sun, like 1 inch of water is inside the home, and can cause like minor damage. But when we talk about moderate damage, so we are talking about 1 feet or 2 feet of water inside your home. So you have a really massive damage in your home. You need to replace all your appliances. So what is the probability of having this? So this, how we shift based on the component failure, we will know what is the probability of being in a slight, moderate, extensive damage state. So this shifting from component to building. How about community? How can we design communities or know the entire functionality for the entire community? So we need to find a way to shift this, and I'm going to explain this later. And research that way will help us to investigate mitigation. How is that? Like you can, like for example, you can invent a new clip between a wall and the roof and see how this will impact the failure. For example, you were able to invent a new clip that can connect the wall with the roof and help with the hurricane, and the vulnerability function become like this. Which one is better? Is this one or this one? Which one is stronger? This new one, because at the same wind speed, at the same wind speed, this has lower, this, okay, let me just, oh yeah, sorry. Okay, so it will be something like this. This will have lower probability, but this will have higher probability of being damaged. At wind speed 50, this will have a probability of being damaged of 20%, but this will have a probability of damage of 80%. Okay, because you did something that add more strength to this connection. Okay, so this is what we call mitigation. So if we were able to scale our research from component to building to community, when you add a change here and it changed the vulnerability of the component, you can see how this impacts the building fragility. And you can see how this, when you do all that to all the buildings within the community, how this impacts the entire vulnerability of the community. Okay, so there's like staging research from component to building to the community will also allows you to investigate component level mitigation, building level mitigation, and also community level mitigation. And when we talk about flooding, we can talk about like, when you know that you have flooding, you sometimes like think, how about I elevate the electronics from the ground? If you have laptops, computer in the first floor, and you have a second floor or an attic, you can move all these components to the second floor. You'll think, okay, how much savings I will have? Okay, you will have maybe $10,000, $20,000 in saving if you were able to like have some blocks and elevate your appliances, washer, dryer, fridge. All this will add up. And when you count all these at the community level and each building is saving like $20,000, we are talking about millions. And we proved this with research, okay? So component level analysis and component level mitigations helps, and we can quantify if we follow this approach in research. Same thing, building level mitigations. You can investigate the impact of renovating the entire building, or making a flood barrier around your building, or using a flood pumps to decrease the water infiltration. All this can help your building. Community level mitigation, like if you will make a levee or like building a retention system that can reduce the amount of water in the floodplain. So all this can help in doing community level mitigation. So approach like this will help to investigate, because it's very easy that you say, okay, I will elevate my appliances and my electronics, and anything when it's touched by water, it will get damaged, and it will help, but how much it will help? We need to quantify this. These functions, these vulnerability functions will help us to quantify, okay? Will help us to know how much savings that we have. Is it worth it or not? Okay. All right, so the research in this area and risk and resilience has three main different areas that you can search at. There's one is called the risk analysis, and there's one called resilience analysis and recovery analysis. As I explained, resilience needs to have a background about the hazard, a background about the exposure, and a background about the vulnerability. Hazards could be, for example, here I was talking about hurricanes. So for hurricanes has lots of components of hazard. Hurricanes come with wind, come with flooding, and the flooding has different types: coastal flooding, fluvial, and fluvial. Because hurricanes, when it hits coastal community, the coastal community is exposed to a surge, like a seawater coming from the sea. But also rainfall comes on the inland community, and this rainfall gets into rivers, and the rivers make riverine flooding. So it also has fluvial. So fluvial is riverine flooding, fluvial is rainfall flooding. The rainfall itself, sometimes it's very huge and makes lots of flooding, lots of rainfall flooding. And waves is one of the most destructive hazards that come with hurricanes. Like they cause structural damage. Surge usually cause content damage because it's just a rising water. It doesn't push the buildings that bad, but the waves makes lots of structural damage. So waves is one of the severe hazards that comes with hurricanes. So if you want to do research in multi-hazard hurricane, you should have a background about all these type of hazards: wind, surge, and wave, and all these hazards. When we talk about exposures, we mean all the assets in the exposed location. And when we say buildings, we mean like residential, commercial buildings, social buildings, a school, hospital. All these we call it exposed assets in your community. If you lose one of these assets, it will impact your community. If a big portion of the residential sector got impacted by flooding, so lots of assets that you lost in your community. And networks as well. So networks, I mean by the transportation network, the power network, the water network, all these assets for the community. If it's got damaged, the community is losing a lot. So the third component is the vulnerabilities. There's different ways to model vulnerabilities. Some people use fragility functions. Some people use loss functions. Like for flooding, the current practice is there's a curve, and you go with the flood depths and tells you how much damage that you'll have. You will lose 20% of your building, 30% of your buildings based on the flood depths. This is a way to determine damage, but there's many other ways to determine damage using fragilities, stage damage functions, lots of functions that you can use. We will learn some about this. So for resilience, resilience means the ability of the community to recover very fast after natural hazards. So yeah, the natural hazard hit a community. So does the community is recovering very fast? Does the community has redundant infrastructure? You have two hospitals in your community. So one of them is damaged, but the other one is working. So this we call redundancy. And are you using the mitigation measures that help you to recover fast? Do you have a long-term or a short-term mitigation measures? So there is what we call resilience-informed decisions, the decisions that you take to make your community resilient. Some of these decisions at the pre-disaster level, and some of them at the post-disaster level. And both of them has short-term and long-term. So there's some mitigation measures at the building level or at the community level. Like maybe a household know that he's gonna have a flooding, and he think okay, I'm going to build a barrier around my building to help my building not get flooded. So this is at the building level. And at the community level, the city itself see that, okay, there's a part of the river that is going to flood a lot in my community. I'm going to show you some slides that shows like there's some location that if you were able to block it, it will make the flood less intense in your community. So this is called community level planning or community level resilience. And here's an example, like if you are using the barriers or you are elevating water sensitive components in your buildings, or you were able to build a flood berms in some location, like you were able, you know that there's flooding is coming from this way, I'm going to block it. And there's other flooding coming from this way. So all this is short, some of them is short term and some of them are long term. The second one is the post disaster, and post disaster is like, okay, I had a flooding, so I have people without homes. All their homes are flooded, so I need to provide shelter. So this is called, so it's not only about the structural engineering, it's also about humans, about people that live in the community. Because when we design buildings to serve people. So we need to have these people not to dislocate. So also you need to secure food, you need federal funds for these people so that they can rebuild their homes. So all this is what we call post-disaster planning. So after the disaster, we need to plan how to get these people back home, either by physical recovery or either by social recovery. Okay, so this, when we talk about resilience, so this will take us to the recovery, and the recovery, and I touched base early versed in this lecture about that you can have your home not damaged, you don't have any flooding or any wind damage, you still have water and you have power, but you don't have an accessibility to your workplace. You don't have accessibility to shopping centers or gas station. You cannot fill your car with gas. So all this impacts your functionality and your recovery. So when we think about recovery of a community, we need to think about all the components that feeds into the services that every household needs. Like you need accessibility to healthcare, to educational services, to your workplace. You need a physical home that is like working, that has power, that has water and sewer and telecommunication. You need to link all these together. Okay, so this is just like kind of overview about the different analysis that you can do in the general realm of communal resilience. Well, let's see an example about a flood risk analysis. So just like to know how this research or how these concepts are like translated into research. Well, for flood risk analysis, I'm going to show an example of one of the communities that we have been working on for like 5 or 6 years and modeling the communal resilience of this community following natural hazards. So this community is called Lumberton. So this is the city of Lumberton here. This is a small big point, and this is how it looks like. And every point here is actually, you guys see like, is it much better now?
Yeah.
Yeah. Yeah. So, and every point here is a building, and they are color coded based on the occupancy. The green is residential, the red are commercial, and there's some yellow, which is schools and hospitals. And this city is in Robeson County in North Carolina. So here's the location with respect to the North Carolina. So for the hazard modeling for this, or for the risk modeling for this community, to do flood risk analysis, we have to go flood hazard modeling. We will have to go through 2 main processes. The first one is hydrologic modeling. So there's a rainfall, and this rainfall is falling on the ground. So we need to know how much is the flow in the main streams. So we call this hydrologic analysis, is to transform the rainfall into water flow. So we need to know how much water flow in each stream. And to know this, we need to have a digital elevation map. We need to know what is the elevation of the ground. Okay. And we need to have a soil map and land use map, because both of these will tell me how much water is deeply infiltrated in the ground and how much water is in the surface. And we do some analysis on the dam and some analysis on soil and land use, and also the dam, to identify where is the rivers at, and what is the river's length, and what is the river's slope, and what is all the basin characteristics. The basin, I mean, we divide the city into basins, like catchment that catch the water. And where is the river in each basin? And what is the basin slope, centroid, and what is the longest flow path? Where is the water is going that long? And based on this and using the rainfall information, we know what is the flow in each stream. And we get that flow in terms of what is called flow hydrograph. The flow hydrograph tells you how is the water flow is changing over time in the stream. If you don't have a severe rainfall event, so the water flow will be constant. But if you have a severe rainfall event, the water flow will jump until the maximum rainfall is gone, and then it will come back. So it always looks like this. It's like very low, and when the rainfall event happening goes very high, like I mean by water flow, like in cubic feet per second or cubic meter per second of water. And then after the event, it goes back down. So this is what we call flow hydrograph. And this, the output result of any hydrologic analysis, is what is the hydrograph of each stream? What is the water flow over time in each stream? Okay. And then we use this hydrograph as a boundary condition for a hydrodynamic analysis. Hydrodynamic analysis transforms this flow hydrographs, this flow into water depths. Like when this stream has this amount of flow, how much of overflow will go out of this stream and flood my community? So they solve a shallow water equation, and then they account for the flood depths and flood velocity in your community. So hydrologic modeling tells you flow, but hydrodynamic modeling tells you velocity and depths of the water, okay? So once you are done with the flow hydrograph, you get the flood inundation, and then you overlay the inundation with. So once you have the flood depths back, you overlay it with the community in a GIS environment. It tells you what is the exposure level of each part of the community, where it hits more, where is the maximum flood depth, and where is the lowest flood depth, and where is the location that doesn't have any flooding, and where is the location that has flooding, okay? And then we use vulnerability functions to identify the damage. And this process is called a flood risk. What we did right now, we did hydrologic and hydrodynamic analysis to get hazard, and from hazard we identify the exposed location, and from the exposed location we use the fragility curves to identify the vulnerability. So we did the three components of the risk: hazard, exposure, and vulnerability. Then we have flood risk. So this is how we apply the concept of risk into flooding. We develop hazard, we identify the exposed assets, and then we do vulnerability analysis to know damage. We studied this community after Hurricane Matthew. So Hurricane Matthew happened in 2016. It started as a Category 1 storm in the Caribbean and intensified as Cat 5 and made landfall as Cat 4 on eastern Cuba and made the second landfall on the east side of North Carolina here. However, it was Cat 1 storm, but the Cat 1 storm brings lots of rainfall in North Carolina. Lumberton is here, which is away from where the storm made landfall, but the rainfall is very hazardous in this area. So there was like 12 inches of rain. It was raining for 2 days, caused severe flooding in Lumberton, North Carolina. So here's how the rainfall intensity look like. So intensity of rainfall is in inches. So here's where is the maximum rainfall happen. And actually Lumberton here in this location, where is the maximum rainfall happen, and this is how the streets look like within Lumberton. So the first thing that we did for this city, we did hydrologic modeling to identify the flow hydrographs in the street. So we need to know how much flow is in this street and how much flow is in the other street. So these two flows will come together, and here will enter to this city and make flooding. Okay, so this is an example of. Here's the boundary condition. The flow comes from here as a boundary condition, and flow comes from here as boundary condition. And here's how the water is getting into the city. This is how we model the hazard. And can you see this gap? There's an intersection at between a bridge, between a highway and a railroad. And here's how the water is coming at this location. Most of the water is coming to the community from this location. And that's what I was talking about. If we were able to plot the water here, we could have reduced the amount of flood damage. So here's actually shows a scene of where is the bridge at and how the water was coming, but not from Hurricane Matthew. It was from a hurricane that happened 2 years after. It's called Hurricane Florence, but it was much worse in Matthew. So Florence was less intense. So you see like here how the flood happens, and this is how the the hydrodynamic simulation look like? And this is what the hazard maps that we need to use to identify what are the exposed assets. Also, sometimes we don't have to model real event. We can model like return period events, like a 100-year event or a 10-year return period event. So this event is a 10-year event. As you can see, is much less flooding. Like the water is this actually the rivers. So the water are within the rivers. So there is no flooding, just like a minor flooding, maybe a couple inches of flooding, like just the streets at some locations are flooded. So if you have a low return period event, so we don't expect that much, like a rainfall that happens every 10 years, a very intense rainfall that happens in a 10 year. So this is how it looked like. But if we compare it with a 100-year event or a 200-year event, it will be completely different because it will be much more intense flooding. So you will find much more flooding inland, and water is getting or overflow the rivers and flood the community. So right now we saw a real event like Hurricane Matthew and return period events like 10-year return period or 200-year return period. And this is what we mean by hazard. The second thing is modeling communities. We need to model communities to identify the exposed assets within the communities. So to model this community, we need data about the buildings, right? So to know what is the exposed asset, we need to know where's the residential buildings. And for example, buildings, we need to know what is the building materials, what is the number of stories, if you can see, building use, what is the foundation type, where's the floor elevation, ground elevation. You need to know all this information about the building to know how vulnerable this building will be. Because if the building is 1 meter from the ground, is completely different from a building 3 meters from the ground. If a building from a concrete is completely different from a building from wood, right? So we need to know all this information. This data can be easily provided by the state, like the state of North Carolina actually have very detailed about the building and it's open for the public. Actually, they can tell you how many nails in the shingle of in each building in their community. But other community doesn't have this data and we need to make an assumptions. So getting the data is very hard. So sometimes we pay to get data, sometimes we get it for free. Sometimes actually we use Google Street Map View and walking in the streets in Google Maps and do it building by building, looking at Google Street Map View and identify, okay, this building is 2 stories, this building has a roof, this building has a hip roof, has a gable roof, and we do this. But this process is very tedious when you have thousands of buildings. But if I have like 300, I can't do it. And this, if you have a 500,000 building, this will be very difficult. But if you have few, you can do it. Let's assume that we have the data about the building. The next step is to identify what we call building archetypes. So what we did is you can have a residential building, but we need to identify the different types of residential building. We developed what we call minimum building archetypes portfolio. We developed a number of building models or building typologies. We call them building archetypes. And these building archetypes is supposed to represent all the different building types within the community. We will develop one archetype that is 1 story and on a slab grade foundation, and it's going to represent all the 1-story building within the community. And we will develop another archetype that is 1 story and on a crawl space foundation, and this is going to represent all the crawl space foundation 1-story residential buildings in my community. So that's what we mean by archetypes. So for flooding, we developed, for this community, we developed 15 building archetypes. These archetypes has 4 residential buildings, 5 commercial buildings like gas stations, strip mall, shopping centers like Target and Walmart, 2 schools, 1-story and 2-story school, hospital, community center like church, office buildings, warehouse, lots of different building archetypes. And we know detailed vulnerability information of these archetypes. We have the fragility function or the vulnerability function or the damage function for each one of these buildings. But the challenge is, how can we know that a specific building in my real community matches these archetypes? How we can say that this specific building here is archetype F1? And how can we say that this archetype F4, that this building is archetype F4 or this building is archetype F5? Okay, so this is a challenge. How we can know this? So we developed an algorithm. So this is actually the archive at 15, and this is some of them, like the names, like one-story residential building on a Starbury college, or F11 two-story school. Okay, so the next challenge is, how can we know that this building is a specific archetype? So to know that a specific building is a specific archetype, I need to know all the information about this building. What is the construction material? What is the roof shape? What is the number of stories? What is the foundation type? All this information. And we developed an algorithm. It's like a for loop. So this for loop goes building by building, and it checks, does this building have this type of foundation? Does this building has this number of stories? Does this building has this construction material? And if satisfies all the conditions, so this building is archetype F1, and then you check other conditions. So if it's one, if it has crawl space foundation, so it's F1. If it has slab grade foundation, so it's F2. So it's an algorithm that has a for loop embedded, and it check building by building some condition and assign an archetype. And we call this mapping algorithm. It actually maps real buildings. So we know that this is a church. So I know that this is a church. So okay, I assign an archetype of a church. I know that this is a school. So I assign an archetype of a school. Okay, based on the mapping algorithm. We did this for many communities. This is one of the example communities that we applied this mapping algorithm to. So this is actually the real building, and this is the mapped archetypes color-coded based on their archetype, like archetype 1, archetype 2, archetype 3. So right now, we were able to develop a model for the entire community, right? The next step is to identify the exposure of these buildings. Which of these buildings are exposed and which of these buildings are not exposed, and how much is the exposure? So the next step is to overlay the hazard map with the buildings. And once you overlay them by spatial analysis, you can identify what is the hazard intensity at each one of these buildings. Some of these buildings will have lots flooding, some of them are not flooded. So that's what we call exposure analysis. You will know what is the flood depth at each one of these buildings. Once you know the flood depths at each one of these buildings, you can start the next step, the vulnerability. Because to identify damage, you need to know the hazard intensity, like wind speed or the flood depths, so that you can know how vulnerable are these buildings. So for vulnerability functions, to develop building level vulnerability functions, we have to start with components. We have to know what is the vulnerability of each component within the building. And vulnerability here, I mean flood vulnerability. What is the vulnerability of your external EC unit? What is the vulnerability of actually this table or this chairs? And if we like the fridge, the appliances, all the appliances, all your furniture, the couches, the beds, everything in your building. Okay, so what we did, we divided the building into components, and we identified the flood susceptibility of each one of these components. Like, for example, this is a one-story residential building on a slab on grade foundation. It has like over 65 components. We have a fragility function of each one of these components, and we use the concept of reliability and Monte Carlo simulation to develop a fragility function for each one of these components. So we have gone through a process, and this process includes, for example, this, let's assume that this is a wall, and this is actually the resistance of the wall. It's a normal distribution, okay? So if the mean resistance of the wall, let's assume it's 1 meter flood depth. So if you were hit with a flood depth that is 0.5 meter, you will have, for example, 50% probability of failure, or 20%. But if you have a 1 meter flood depth, so you might have 80% failure. But if you hit with 3 meter flood depths, it might have 100% probability of failure. And that's what we are going to learn, how we can calculate the probability of failures of the components, knowing the distribution of the resistance, on what is the probabilistic resistance of these components. Yeah, so this is an example that shows you, for example, sometimes the uncertainties, we are not talking about real damage to the component, like we are not talking about the columns. We are talking about like an AC unit or an electrical socket, something like this. If it hits with water, it's gone. So how we can know this? So uncertainties can be in the elevation of the AC unit. Sometimes we see this AC unit is on the ground, right? Sometimes some people put it like 10 centimeter or 20 centimeter from the ground. Some people put it like 80 centimeter from the ground. So there's uncertainty in the elevation of this AC unit, right? So if we were able to propagate the uncertainties in the AC unit and know the distribution, like we know the mean level of the AC unit and the standard deviation, we can know what is the probability of failure of this AC unit. Okay, so that's what we do for every component in the building, like AC unit, appliances, furniture, and we know that, and we were able to identify what is the probability of failure of each component. But once you identify the probability of failure, as the next step, what is the impact of failure of this component on the total performance of the building? Maybe you will, okay, if you don't have an AC, you can live without AC for 2 days, so it's not that big deal. But if you don't have, for example, all the appliances are damaged, stove, fridge, and your furniture, like couches, bed, you cannot live. Okay, so we needed to create what we call damage states or damage scale or limit states. And we call them insignificant damage, like this. You have water around your home, but you don't have damage. Or maybe some damage here in your front patio or some components. So we call it insignificant damage. But some damage is slight, like you have a 1 inch of water that damage your carpet, but your furniture is good, your appliances is good. So what you will do, you will hire a contractor the next week and you will change your carpet. So what we call this is a slight damage. Moderate is more intense, like you have 2 feet of water, and this 2 feet of water is going to damage all your appliances, and your recovery is not going to be a week. It might be months. To get funds, to get money, you might need $100,000 to get recovered, replace all this drywalls, and get new appliances, new TV. And damage state 3 is extensive. You have like 2 meters of water inside your home, and your building really has extensive damage. So to know the building is inextensive or complete or moderate, you need to know what components are damaged. So you need to have a list of all the components, and you assign all these components to damage states. Like you will have here, all these components are in damage state 0, all these components are damage state 1. And based on the damage of all these components, you can identify what is the level of damage for your entire building. Okay, so that's what we do. And that's actually what you should do if you are investigating building level performance. Because building level performance is not only about one component, it's about all the components within your building. So this is just an example of just like showing you how much information that we have about our building, the HVAC pipes, the garage drywalls, the AC unit, heating units, baseboard, carpet, refrigerators, all the components in the building. We identify all the damage to all these components, and based on this, we know what is the damage to your building based on the flood depths. Yeah, so this is a bunch of the final results for a 2-story residential building. This is actually a real building that shows that all the components that we included, and this is 100 component fragility curve for a cabinet, for an AC unit, for a drywall, for everything in the building. And based on these components, we were able to know what is the probability of a building to be in insignificant, slight, moderate, extensive, and complete damage state. And as you can see, when the flood depths increase, you have much higher probability of being in extensive damage state. But if you have a 1 meter flood depth, there is no extensive damage state, just like the red is here, and the probability of being in red is 0. And extensive, this is complete. Complete start at flood depth 3. And since this is a 2-story building, so it's a 10-meter height, so you have almost the first story is gone and it needs to be replaced. But if the water is much higher and you have your entire building submerged with water, it's complete damage. So all your building need to be replaced. So this is just an example shows how the component fragility look like and how's the building fragility look like. And I mean by fragility, vulnerability function, damage function that can inform the damage based on the hazard intensity. And also this shows how we were able to convert component fragility into building fragility. So as I told you, there's some components that tells us what is the damage to your building. And when you have a structural damage, so we are talking about foundation, about walls, about roof, all this is structural damage. And when your structure is damaged, it doesn't matter how much component you have it damaged, your building is entirely damaged because the structure needs to be like demolished and get a new structure. So I'm showing here an example of 5 components that tells us what is the probability of being in damaged state or complete damage. So you need to convert this 4 or 5 curves into one curve. So we average, or not average, we do a weighted average of this. Based on, you can do it based on the importance of the component, but what do you think is the most critical when you weight component damage? I believe the price. Because if you have a damage to the fridge that is worth $1,000 is completely different if you have a damage to the roof that is worth $100,000, right? So based on the price of the component, we weighted them, but actually you can weight them based on how much time they take to recover. Maybe you have a drywall damage that is worth $10,000, but also you have an appliances or a computer that is worth also $10,000, but the computer you can buy it and get it in the same day. But a drywall, it's a construction job. It needs a permit, it needs a time, it needs a contractor. It might take months or 2 or 3 months. So you can weight on different things. But what we did here is based on the price, and we were able to get one curve based on these. And actually, this third curve, we weighted like 36 components to get this curve based on the price. Yeah, same thing. So this, when we talk about damage, so we want to transform this damage. I don't want you to tell me if I have a slight or moderate or extensive damage. I want to tell you how much I lost in money, how we can transform this into money. Same thing applies, like it also needs probabilistic concept because it's not a constant price. The price of the markets keep up and goes, and also based on the contractor, it's based on the market, it's based on your building itself and how quality that you need it. So we need to propagate uncertainties in the replacement cost of the components. So for example, I get this chart from Home Advisor that tells you that most of the homeowners in the US are spending between $900 to $2,700 in replacing their home vans, like if they are going to ban their homes. So there is a normal distribution and there's uncertainty in this cost. So what we do, we use this distribution to get a replacement cost vector, like to get a random 1,000 simulation of the replacement cost of your entire building. And then we use this, and if you know the probability of failure of your building, if you multiply the probability of failure by the replacement cost, it tells you how much that you are going to lose. Like if you have a component worth $10,000 and you know the probability of failure is 10%, you multiply 0.1 by 10,000, so you have $1,000 of loss because it's 10% probability of loss. But if you have if you know 100%, like probability of failure of this component is 100%, and it's a $10,000, so you are losing at 10,000. Okay, so this is how we transfer probability into a cost. All right, so actually I was just like trying to inspire you guys about how this research is working, and I might extend it to the next lecture because I need you to understand the importance of this in your research, or you can actually expand this in your research. I believe this is very important to inspire you because if you felt like motivated, you can add much effort in this class and try to learn more. Because I'll try to cover as much as I can, but you will have to do your part. You will have to go read publication. I might give you some publication to read, so you will have to do your part in this class. So we will be continuing this class like next, like it will be Wednesday. So this Wednesday on this and how the work and risk and reliability is going to help you in your research. So does anyone have any question?
I have a question. Slide 24.
Okay, let me. Yeah, this one.
Yeah, how will you determine the damage ratio to be able to identify what the level you're in?
Okay, so let me go here. Okay, so once you know the components that are going to be damaged, like for example, you have 6 components, and you know these are in damage state 1. We price these components. We know how much does it cost these components. Actually, we have the mean unit price of each component and what is the units that we have. Like if you have a drywall, how many square feet of drywalls do you have and how much the 1 square foot goes. And this is a mean and a standard deviation. So finally, we have the mean and standard deviation of the replacement cost of each component. So we know the mean and standard deviation of the replacement cost of the entire damage state. And so we have it for damage state 1, 2, 3, up to 5. So this is how we get these values. And it's a range because it's different from a building to another. If you have a hospital, it's completely different than a school, completely different than a regular residential building.
Yeah, so determine what the damage state I'm in and divide the cost of the building, the components that are supposed to be damaged by the total cost of the building.
You mean this one?
Yeah, no, to determine like what actual building.
Yeah,
will be
okay, I got
damaged state,
your point.
what
Here?
damage ratio.
Yeah, so what we did here is that we have the failure probability of the component, okay? And we weight each component based on the replacement cost of the component over the total replacement cost of the entire damages. Like if you have damage state 4 is a worth of 10, 100, or $100,000. One component is 10,000, one component is 30,000, and another one is 60,000. So the 60,000 will be able to shift this curve more than the 10,000 component.
So the submission gives me the damage ratio.
Yeah, the summation gives you the damage ratio for the entire damage. Does anyone have any other question? All right, so see you guys on Wednesday.
I think about